In section 14.5, we are going to discuss reaction mechanisms. Some chemical reactions happen in just one step, with the old bonds breaking and new bonds forming during an infinitesimally brief time, or the transition state. But many reactions involve more than one molecular event and are best described as a series of elementary steps, with each of which has its own transition state. So a portion of the reactant molecules react to produce a short-lived unstable intermediate form, and the intermediate reacts with the remaining reactant molecules to produce the final product. Let's consider this hypothetical two-step reaction. We have AB plus C becomes AC plus B. This doesn't just happen where it creates everything we want. It happens in two steps. In the first step, we have to break the AB bond, and in the second step, we have to form an AC bond. So let's look at this graph. We're going to start with our reactants, so AB, and we need to break the bond between them, which is going to require a certain amount of energy. Then we're left with A plus B. So then we're going to add C into the solution, or it was already there. So A and C is now going to have a bond formed. So we're going to be forming this bond, and notice that the energy required is a lot smaller than the energy required to break that bond. So we then formed A and C. So we're left with A, C, and then B is just left over in solution. So that's how a two-step reaction will look if we're dealing with activation energies. Together, these elementary steps make up the reaction mechanism. One step is always going to be slower, and that is going to be your rate-determining step. The sum of these steps also equals the overall chemical equation, and the experimentally determined rate law describes what is happening in the rate-determining step. Here's an example of an elementary step to make an equation. So let's consider the two-step reaction of nitrogen dioxide with carbon monoxide. So in the first elementary step, we have NO2 plus NO2 becomes NO and NO3. And the second elementary step, we have NO3 plus CO becomes NO2 plus CO2. It's a lot. The overall equation is NO2 plus CO becomes NO plus CO2. So first things first, we need to eliminate anything that's on both sides of the arrow. So on the right-hand side, we have NO3, and on the left-hand side, we have NO3. So because we have both of them on either side, you're going to have to eliminate it because they equal each other out. We also can eliminate one of those NO2s because we have an NO2 on both sides. So whatever is left over, we bring down into the overall equation. And that's how we're able to calculate the overall equation. Another thing to note, that anything that is produced and consumed, so produced in the first step, consumed in the second step, is going to be your intermediates. Here's that exact same reaction we just covered. NO2s cancel, NO3 cancels, and that's the overall reaction mechanism. We're going to go over intermediates again. So note that NO3 is produced in the first step and consumed in the second step. That's why it's going to be considered an intermediate, because intermediates do not appear in the overall equation. And we also discussed that when we had two molecules of NO2 required for step 1, but because NO2 is produced in step 2, only one molecule appears in the overall reaction. So you might be asked, what are the intermediates? Well, anything produced in the first step, consumed in the second steps, is going to be our intermediates. Example 14.15 says the decomposition of N2O into O2 and N2 is thought to occur via a two-step mechanism shown below. Write the overall equation for this reaction and identify any intermediates. Let's look at the equation. So step 1, we have N2O, and that's turned into N2 and O. And then step 2, N2O plus O becomes N2 and O2. So anything produced in the first step and consumed in the second step is going to be our intermediates. So that's going to either be N2 or O. And if we look at the second step, that's going to only be O. So oxygen is going to be our intermediate. Also, intermediates are unstable, and oxygen by itself is highly unlikely. Oxygen is very comfortable being a diatomic molecule, so O2, so that's why it's also going to be an intermediate. So you're going to have oxygen on both sides of that arrow. That's going to cancel. There is nothing else that's going to cancel, so whatever is left over, we're going to bring down. We have 2 N2Os on the reactant side, and that becomes 2 N2 plus O2. So I'm just adding them together. So N2 plus N2 just becomes 2 N2.